Okay, good afternoon, everyone, and welcome back to the post-lunch session, and welcome back to the second Chandrasekhar lecture by Professor Joel Moore. So today he is going to tell us about the fates of pure many-particle systems, some hydrodynamical limits of spins and qubits. Over to you.
Thanks very much. So this will be about quite different things than the first lecture. I only have, I think, 2 slides in common, and those will go by very quickly near the beginning. So there are really 2 parts to the talk. One is about a quick introduction to the world of one-dimensional hydrodynamics, where there are certainly some experts here. And it turns out that a very old problem, one of the first non-trivial problems in quantum matter, maybe we didn't really understand the dynamics until about 2019. And I was very surprised. The reason why I wanted to talk about it here, by recent progress using quantum computers. It's one of the first scientific problems, the first one that I cared about, where new quantum devices at IBM and Google are maybe helping a little bit. I wouldn't say that they have a dominance or even a clear advantage over the best classical approaches, but somehow this problem that I'll talk about, which many of us were interested for its own sake, is also a good problem for current quantum computers. And then the second half of the talk is about higher dimensions and things that are really at the frontier of what we can do by any method. And I'll explain why we do those, but why they're still hard. So this is work with a different set of characters from what I talked about before. And I'll try to thank them as I go along. But again, most of the theoretical work was people who were at some point at Berkeley on the left side. And in this talk, I do want to get to some surprising and exciting experimental results. The ones up here are sort of the traditional condensed matter ones that I was involved in. All right, so this is the first of the 2 slides. Last time I mentioned that a nice thing about condensed matter is that we make new particles, but one thing that we don't have very good examples of emerging in condensed matter are new kinds of gauge fields. And I'll talk about one strategy to try to make that happen toward the end of the talk. But I will talk about very much this remarkable fact that in a very simple quantum many-body system, you can have 2 kinds of emergence. You can have a new kind of particle, which was known for a long time to happen in one dimension. The so-called spin-on was discovered some time ago in spin chains, and you could say it was more or less predicted by Bethe a very long time ago. But there's also a new kind of fluid, and exactly what kind of fluid emerges in some spin chains is the main recent topic I want to build up to. So I won't cover that much theoretical work from the last 2 or 3 years. There's been a real explosion. I'll basically cover the theoretical work up to about 2020 or so, and then some surprising experiments that have happened since then. So when I say a new kind of fluid in the Heisenberg spin chain, this talk is meant to start off somewhat pedagogically or accessibly. I'll remind you a little bit of other kinds of fluids and what we might normally expect in a spin system. Then I'll talk about what actually happens. And one reason why people from Google and IBM and so on care is that what we would call a chain of spins, they would call a chain of qubits. It's almost the most natural problem you could make of interacting qubits. And the dynamical surprises, I'll try to explain a deeper reason why they care, which is that with enough control over a spin system, you can in principle build a computer that is even more powerful than we think quantum computers are likely to be. So I have a couple of interludes on why, once we go away from sort of translation invariant pure systems to allowing things to vary in an arbitrary way, you get to computer science questions that have stimulated a lot of interesting work. And then in one dimension, I mostly have successes to talk about. The second part of the talk is about a very old problem in higher dimensions that is still not really solved, which is to find clear evidence of a spin liquid, a topological spin liquid, and I'll motivate why we care and why it's hard. But I will talk about what we think is some progress on basically Anderson's original idea of where to look for a spin liquid, which is triangular lattice antiferromagnets. And one theoretical approach there that leads you to a gap state, but maybe even bigger but less well understood would be a kind of gapless state with emergent gauge fields. And that's where I'll wrap up, because that's a problem that there are perplexing or emerging experiments, but there's still no very good predictive theory. So I'm going to be a little bit quick with the introduction, but as before, I've only prepared about 75 minutes, figuring that with questions and discussion, that will fill out the hour and a half. So do interrupt if anything is unclear. But very briefly, one spin is fairly simple. We can represent it on the Bloch sphere. Things start to get a little bit more interesting when we go to two spins. And of course, one spin half is one qubit, one two-level system. When we go to two spins, some states are simple, like the ferromagnetic ground state is a product state in the sense that if I give you this wave function and I ask you, what is the wave function on spin A? There's a well-defined answer. You could say it's up. If I go to a singlet, though, that's about our simplest physically arising example of an entangled state. If I ask you what is the wave function on spin A, there's no very good answer because you have to use a density matrix. You have to use something with an entropy. So even this was a pure state, simplest possible or complete description of two spins, because it's pure, it doesn't imply a pure state description of each of the pieces. That's entanglement entropy. So things get hard. The reason why quantum magnets are interesting is that the singlet is a nice happy state of one antiferromagnetic bond, but we can't simultaneously put all the bonds of a general system into singlets. One spin can only form a singlet with at most one other spin. So that motivated Anderson's idea of a spin liquid, which is maybe those singlet bonds kind of fluctuate in a liquid-like way. But before that, there were other kinds of versions of this spin problem that we'll talk about very briefly. So this is what I said about entanglement producing entropy. This naturally happens in insulators, and I'll remind you at the end how the Hubbard model is one way to get to spin Hamiltonians. But for now, I'm just going to start off writing down natural spin Hamiltonians and playing around with them. If we had a single axis for the interactions, that would, of course, be the Ising model. And what I'll talk about, this is a little bit of a lie. It won't happen for classical spins with nearest neighbor interactions, but there are classical versions with somewhat exotic interactions, like logarithmic interactions in the Ishimori chain, that will give you some of the unconventional hydrodynamics. But classical spins can be very hard if I get away from uniform Ising-like interactions. So that will be one of my first interludes. So as I mentioned, since the subtitle or this meeting is about the age of quantum information, here's why computer scientists started caring a long time ago, even about classical spin models. And in particular, Cook had the idea of an NP-complete problem back in the 70s, which is that maybe you have one problem that is so hard and so general that many other hard problems can be kind of encoded in it or programmed in it. So NP-complete means not just hard, but kind of general. And finding or constructing a low energy configuration of the classical Ising model with arbitrary interactions. So these Wij are some interaction weights. The Z's are just plus or minus 1. And if I ask you to find a configuration of the Z's with energy below some amount, that can be fairly hard as this energy that I'm looking for gets close to the ground state. In fact, it's NP-complete, but it's easy to check. So the sense of these problems is not only that they're hard to do, but they're easy to check. The analogy made in this slide by my student Veer, former student, now faculty at Rice, is it's much easier to listen to music and appreciate that it's good than to compose music that is good. It's much easier to check that someone has given you a low energy state of the Ising model, because computing this is just polynomial time, than to actually find that low energy state in something like a spin glass problem. So that's a sense of what NP-complete problems are. And there was Richard Karp, a famous computer scientist from Berkeley, who actually showed that some very large number of problems, including this one, I think something like 21 problems he rapidly showed were in this NP-complete class. So this actually led to an idea for a quantum computer. But in practice, it lets you understand, there is some conservation of difficulty. We suspect that even a quantum computer is probably not good enough to solve all NP-complete problems. But there is, an interesting branch of computer science that is about defining how relatively hard different problems are. It's very hard to prove anything, so we can't actually prove that, factoring or even NP-complete problems are harder than problems in P. Someone could, in principle, find a polynomial time problem tomorrow. This is called the question of whether NP equals P. But that doesn't seem very likely after all these years of work. So we have to take a few things on faith, even in theoretical computer science. So to kind of reformulate what Karp said in quantum language. This is something you could think of just as well as a quantum model with quantum spins, but they're Ising spins now because everything commutes with each other. And if I asked you to find the ground state of that, one way you might try is to start with a simple state and simple weights and try to adiabatically evolve the system so that you go from simple Hamiltonian and simple ground state to complicated Hamiltonian and complicated ground state without closing the gap. So where does the hardness come in? This was the original motivation for the D-wave quantum computer. The source of the hardness is that the gap becomes exponentially small along every path to reach some very complicated ground states. So adiabatic quantum computing, it works in some cases, but maybe it doesn't work in most likely the hardest cases. But there is still something here that turns out to be more generally true, which is when we look at translation invariant Hamiltonians, in general, as we get to more complicated Hamiltonians and more interesting ground states, those seem to correspond to more powerful computers when we go to generic interactions. And I'll come back a little bit later to why that, well, to at least, I don't know why it's true, but 2 examples of that. All right, so now let's talk about how spins behave in most materials, which is relatively simple, and that will build up to this surprising idea that spins behave in a more complicated way in spin chains. So if I have a conserved number of particles, say, the simplest equation you might write down, at least with left-to-right invariance, is diffusion. Number of particles is conserved, and as I think you all know, that will give me some spreading Gaussian for a solution. If I want to think about what happens in a magnet, there are many magnets where some direction of spin is approximately conserved. So total SZ, let's say, commutes with a Hamiltonian. Then you might expect, and indeed in many materials, the dynamics at high temperature, say, gives you some kind of spin diffusion. And aside from the Gaussian shape, one thing to notice is that I have 2 powers of space and 1 power of time. And that's a dynamical critical exponent of 2, the way I'm going to count it. So this dynamical critical exponent z is how many powers of space do I need to correspond to 1 power of time, and diffusion is z equal to 2. If I had particles moving, say, freely with the velocity, that would be like distance linear in time, and that would be z equal to 1. So, yeah, so here I haven't really assumed, I haven't talked about what the dynamical process is or what the Hamiltonian is. But in practice, yeah, if I'm in higher dimensions and I have no special symmetry or anything, this is what I will get. I might not get this if I had very long-range interactions, and I have an example of that actually in the last lecture tomorrow. But for generic short-range interactions without integrability, with no conserved quantities other than energy and that, this is kind of generic, I would say. So I will talk about some specific Hamiltonians that either do this or don't do this in a second, but definitely above 1D, this is what you should expect. But as an example of how, when you have more conserved quantities, hydrodynamics can get more complicated, maybe the simplest example, or the most historically important example, was these 3 hydrodynamical equations. And the reason I've got 3 is something like a simple fluid, gas, say, has conservation of number, reflected in this continuity equation, conservation of momentum, and conservation of energy. And maybe it's important to say a little bit, roughly, about when these equations are valid and when they're useful. So there's definitely assumption of local equilibrium. Basically, I'm assuming that the local state of the system is well described by things like average density, average velocity. I'm ignoring fluctuations, except those that contribute to the energy. So this is assuming some kind of local equilibrium, but that usually only takes a few collision times to set up if the system is dense enough. So if you want, I've assumed that I've reached local equilibrium and that there's a notion of a fluid cell that has enough particles in it that fluctuations are small. And these equations then describe a very large set of timescales, basically from local equilibrium up to maybe global equilibrium. So something like, the atmosphere or whatever, these equations work for many, many orders of magnitude. So an example of when they don't work, and the basic way I want to present the story is to say a little bit about why some spin models are special and why you might expect them not to show diffusion. And we knew that they were special a long time ago, but exactly what they do turns out to be surprisingly hard. And there was a set of discoveries, I think, starting maybe in 2011, by a lot of people that led us to understand, what does happen. But let me remind you of why these spin chains are special and why we thought we understood them completely, maybe until 2011, at least some aspects of them we did understand. So there are two simple examples of models that have an infinite number of conservation laws. So you might expect any hydrodynamics, if I were going to use Euler equations, would require an infinite list of Euler equations. It happens that there are two examples that are not that hard to create in the laboratory. One is, if I just took the Bose gas with delta function interactions, that might be the simplest example. That's the Lieb-Liniger model. And the one I'm mostly going to focus on is this so-called XXZ spin chain. So I've got a chain of spin halves with nearest neighbor interactions that I allow to be uniaxially anisotropic. So if I just had JZ, that would be the Ising model, which is pretty easy to solve in 1D. If I just had JXX, that would be the XX model, which, as a fun exercise, if you've never done it, is actually solvable as free fermions using the Jordan-Wigner transformation. And when I have both JX and JZ, then it's harder, but it does have a solution through the beta ansatz, and I'll remind you of the spirit of that without getting too much into the details. And if we made the system random, we could get other things to happen that I might touch a little bit on in my last lecture. But for now, this is the XXZ spin chain, and the Heisenberg point, which is maybe the one that occurs the most in the laboratory, at least in solids, turns out to be the most interesting point in some ways, and that's just the isotropic one, JZ equal to JXX. All right, so I'm not going to get very much into the beta ansatz technique, but very briefly, one way to understand why these are special, and I'll try to step back a moment and give you some physics underpinning for why this is true. But if you just want an algebraic fact that these spin chains satisfy, but most spin chains would not, like if I added additional interactions, you can make an infinite list of conservation laws of things that exactly commute with the Hamiltonian. And just to explain the notation, when you see a poly matrix with multiple indices here, that means the product of polys on three successive sites summed over all the sites of the lattice. So I have some conserved charges and conserved currents, and you can see that as I go down the list, I keep getting longer and longer strings of spin operators, but they're all sort of sums of compactly supported strings of poly operators. And that's how we thought conservation laws worked in the XXZ spin chain. So what makes them special on a more general, physical level? Because it turns out that some of the new picture of hydrodynamics actually just reflects what we understood maybe as the physics of integrability. And to explain that physics very quickly, it actually starts already with three particles. And I'm going to express it. These bits of text are from a nice book by Sutherland. I'm going to start with the Lieb-Liniger model, which is, again, bosons with a delta function interaction of strength C. So C equal to 0 is free bosons, and as C goes to infinity, this turns into free fermions. What happens in between is quite interesting, but you can understand what Beta did for the Heisenberg model, actually when he was a graduate student, I think in 1931, was effectively write down a trial wave function. When the particles are separated from each other, we could ignore the delta function and think about plane waves. So let's try a product of plane waves of all the particles with some momenta, and some factor that when I permute the particles gives me some number to multiply that configuration of the plane waves. So when I start plugging that in general, if I tried to do this with an interaction other than the delta function, it wouldn't work. But with the delta function, I realize that there's a relationship that happens once I start trying to check that this wave function works for more and more particles. And already with 3 particles, there are 2 things that it seems like they could be different, but they turn out to come out to be the same. And the deep mathematics of this is usually called the Yang-Baxter equation, or if you like, 2-dimensional lattice models, star triangle relation. The basic physics of what's going on is that, okay, in 1 dimension, 2 particle collisions with energy and momentum conservation are pretty simple. The 2 particles will come in and the same momentum will come out. But if I had a finite range interaction and I had many particles come together at the same point, there would be something complicated happen and different momenta would come out. Here, when particles come in, the asymptotic momenta that come out are the same, and things effectively are like a product of two-body collisions. Everything is independent of the order in which those two-body collisions took place. That's represented by diagrams like this, and it's actually carved on the wall at the Simons Center for Geometry and Physics, which is one of the places that Professor Gopakumar listed as the peer institution for ICTS. So and they on that wall, they have maybe the 20 most beautiful equations in mathematical physics or something, and that made the list. So getting back, to the history maybe of what happened here, the ground state of the Heisenberg chain was solved by Bethe basically by something very like what I described doing with bosons and Lieb-Liniger, which is start with the ferromagnet, like all spins up, that's a simple state. If you flip one spin, that will kind of hop around, that's like a particle. If you flip 2 spins or 3 spins or whatever, you basically build the antiferromagnet by flipping spins from the ferromagnet and realizing that a very simple wave function applies to those spin flips. Now, even though the ground state was figured out in 31 and the thermodynamics was figured out, the thermodynamic beta ansatz in the 1970s, in other words, the free energy at any non-zero temperature, say, it seems like everything happens in about 40-year intervals. It turns out that there's a whole another list of conserved quantities that are the ones that matter for the spin dynamics. And that was noticed really in a nice paper by Thomas Prosen around 2011. And that really explained some puzzles that people had been disagreeing about, such as whether there is ballistic transport, a non-zero Drude weight, in this in XXZ spin chains, let's say. It was known energy is much easier, but spin transport was hard. If you like, the reason why these conserved quantities had been missed and why they were important, they were missed because they're not easy to write down. In fact, they're not sums of compactly supported strings. They're rather like sums of kind of an envelope of spins. So it is quasi-local, it decays with an envelope exponentially, but it's not like just a list of 5 spins or something. So you generate them on a computer, they're quite impressive technically. The reason why they matter so much is that all the conservation laws we had before, they kind of had symmetries of the energy, if you like. They couldn't contribute to a current of spin. Yes. They exist everywhere in the XXZ. That's right. And in fact, the spin Drude weight still vanishes at the Heisenberg point, but you can use those quantities to get its value elsewhere. And just to clarify one thing, in general, there's a charge list and a current list, but I think the magic you're mentioning is that for XXZ, one of the currents is also a charge. Basically, for the Heisenberg model, for example, the energy current also appears in the list of conserved charges, but I think that's the only one that appears in both lists. There's a different sense of a hierarchy, but yeah, the charges and currents, there's something special that you can use to get a lot of results without too much work, which is that P2 equals minus 2Q3. Alrighty, so what I want to now give is kind of a physical picture that doesn't work at the Heisenberg point, and most of the recent excitement is about the Heisenberg point. And the picture I'm going to give doesn't capture everything. I will maybe comment with a couple of words on the things that it misses, but I like it because I can draw pictures and because you can understand it from something you learned, I think, before, which is the Boltzmann equation. And actually, this kind of equation has a history in classical soliton physics. So effectively, the fact that this works, and I'll try to convince you that it works not by a proof, but by numerics, the fact that it works is a sign that if you don't look at fluctuations, and you look at sort of the right things in the long time limit, the dynamics of these quantum spin chains is well given by a classical picture. So the form of the equation, and this general area of dynamics and integrable models in the quantum case, was really brought to a renaissance by these 2 papers around 2016. So the way I will represent it is it's like a Boltzmann equation for the one particle density. So if you remember your Boltzmann equation, which is how you can sort of derive normal fluid equations, you've got a one particle density at some, let's say, momentum, space, and time. Normally there would be collisions that would randomize the momenta, but in integral models, we already said that sort of asymptotic momenta are conserved, so there are no collisions. but the streaming term is modified. So for example, in Abhishek's talk, we saw a use of this for free particles where you could move the velocity outside the derivative because it didn't depend on x. But here, the velocity is going to depend, the velocity for one particle at space-time point xt is going to depend on some integral over all the other particles, all the other momenta at that space-time point. And I'll try to give you a few pictures of why this is a reasonable thing to do. The detailed form of the integral is what, for complicated models, is quite complicated and requires solving some beta equation, but for a model of hard rods, it's very simple and can be done explicitly. But that's what changes from model to model is the form of this V. So this is an integral differential equation, but it's just one equation. It's sort of, I would call it kinetic theory, but I think people in the field tend to call it generalized hydrodynamics. This one equation is enough to describe something like that infinite list of Euler equations would give you. So even if it's a hard equation because of the integral in V, it's not that hard. But the basic idea of this equation is that the only way particles interact in these integrable models is that they're moving along. When they hit each other, they delay each other by a little bit, and then they continue onward. Or in a quantum model, they phase shift each other. That's what collisions do in 1D. But there's an old idea of Wigner that phase shifts, energy-dependent phase shifts are like a delay. But without further ado, I'm not going to talk about the numerical method and even very much about other checks and so on. I just want to show some pictures and explain one setup, because these are two techniques that couldn't have been done when I was in graduate school, say. So the two techniques are density matrix normalization group, kind of microscopic simulation of the spin problem using matrix product states. And the solution of that hydrodynamical equation I wrote down on the last slide. The horizontal axis is the space, x direction of the spin chain, and the vertical axis is energy density. So at time zero, what I've done is kind of heat up the spin chain. And the difference between here and here is different temperatures. So these are all interacting, but still easy plane. It's like delta of 0.5 or something like that. And what you can see is that even though you might not trust either one of these numerical methods on its own, they're making very different assumptions and errors and all that. But they agree very well. You can see the lump of energy spreads, but it spreads very differently depending on the parameters. This is, again, a hot lump of energy spreading into a cold vacuum. Here, this is a two reservoir problem, hot left and cold right, say. And just zooming in, it works better than 99.9% of the numerics we ever have tried to do in my group, I will say. So it was very satisfying. So that approach, the good news is this easy plane approach, if you just care about kind of the leading order behavior, which is all I'm going to talk about here, no fluctuations, it shows that there are effects of interactions, but that this kind of semi-classical equation captures them very well. But it doesn't work. This is intrinsically a ballistic scaling equation. It doesn't work once we get to the Heisenberg point when I restore the SU2 symmetry. I should say that, as I mentioned, there's been a huge amount of work. One-dimensional hydrodynamics is maybe the most beautiful class of many body problems out there, and I feel I can't do it justice at the level of this lecture, and I don't claim to be an expert, but the world's expert, Herbert Spohn, I'm happy to say, is in the audience. So if you have further questions about all the exciting stuff that's happened the last couple of years, I will try to answer, but I may point you to him. So more on this picture. The way to think about it in something like the nonlinear Schrödinger equation, so that's a one-dimensional integral partial differential equation with solitons. And what makes some PDEs special is that you can make a lump of energy that will propagate along, but you can do that in a lot of equations. What's special about integrable equations is that when two of these lumps come together, they distort each other for a while, it gets complicated, but then they separate and go on their merry way. They are like particles, except that if you look, the dotted lines are the trajectories the particles, the solitons were on before their collision. Effectively, they deviate from those trajectories. That was that delay effect. So they've come out with the same velocities, but there was kind of a shift of time. And in quantum mechanics, I can't draw as nice a picture in quantum mechanics, but basically an energy-dependent phase shift, which is what is kind of the ingredient that goes into the beta equations to solve the problem, that's really just a time delay. So that's kind of how you can understand why the same equation works in the quantum case and in the classical case. So maybe, yes? Yeah, that's right. With integral models, I would say that there's a notion of momentum. So that, like, normally that term would be two momenta come in and two other momenta come out. But that doesn't happen in integral models. I think that's a general feature of integral models, that there's a notion of asymptotic momenta that come in and come out the same. There will be a collision term. So I actually have done a little bit of work, and other people have as well. I can tell you a little bit about how, okay, so there's like a short time regime where you could start with this equation, but in general, if you add collisions, it will ultimately cross over to diffusion because you won't have as many conservation laws anymore. So that's to say, like, you know, if you added, what made this equation work in a sense was all those conservation laws hiding in the background, and I'll kind of illustrate that for Lieb-Liniger in a second. Whatever scattering you added will break those. That's why it breaks the integrability, and that means at some time it will cross over to diffusion, and exactly what that time is, I can tell you for the Heisenberg chain a bit later, maybe. No, I mean, if I were going to add general non-integrable perturbations, I could justify adding an actual Boltzmann-like collision term on the right-hand side. You know, that would be like, you know, so that's integral over three other momenta, one of which is the other incoming, you know how the collision term in the Boltzmann equation is like a rate in minus a rate out? So I could just write down the standard Boltzmann collision term on the right. Yeah, so everything I'm going to talk about is pretty specific to local interactions. So there are integrable models with non-local interactions, and those actually will not be as well, they'll often be very interesting, but they won't necessarily have quite this description. So for example, something that I think people here have worked on, there's a class of integral models that have inverse square interactions, like 1 over r squared. And then, you know, even in the isotropic case, the scaling is very different. You won't get the kind of KPZ scaling I'm talking about, you'll just get ballistic scaling. So I think there is an interesting body of work on integrable longer range interactions. And some things carry over, but some things don't. It's sort of interestingly different. Exactly, yes. Well, so I guess because there are, you know, I don't need, because I set the collision term to 0, if you like, you know, because I would say why does that happen is that the one particle distribution, you know, because the asymptotic momenta are conserved by collisions, I think would be the simplest way to state it. So in other words, however many particles come together, the momenta coming out are the same as the momenta coming in. So if you like, I mean, this, you could view this as, yeah, the part that appears, you know, the existence of other particles only matters through this term. And it's true that all the other momenta matter. So this is an integral. So I mean, if you like, it's closed, but only once I realize that this is an integral over, you know, all the other k prime. So there's a kind of closure that was done in the integral, I guess.
So earlier you said that talked about this quasi-local charges. So that exists at all values of delta or Jz. Then why is it that the spin Drude weight is non-zero only in the gapless phase? But
because, yeah, so there's something, the formalist statement of this would be the Maser bound, but I have to ask, you know, what is the overlap of the spin current with the charge, with the conserved current, and that can vary.
when you looked at when you showed the DMRG data, so the way you injected the energy at the center was to locally heat the system, but does the transport and the velocity of the ballistic propagation of the two blobs, does that depend on how you inject the energy? If you had put some other operator at the center and injected additional energy, would the profile change completely?
I think that if you have reached local equilibrium, it should be the same, but I think this is a good way to kind of break up the two processes in dynamics of probably any model, but at least integral models in a standard fluid, which is that there's kind of there's a quench or, you know, pre-local equilibrium time scale when you wouldn't use hydrodynamical equations in general until the system has reached local equilibrium. And the version of local equilibrium for integral models is something called generalized Gibbs ensemble, which I will have in a second. But basically, once you've reached local equilibrium, that's when your hydrodynamical description you hope will be valid. So if I had set up, I think any process that led me to local equilibrium would give me the same answer. But if I started with something that was not in local equilibrium, things would be different until I had reached local equilibrium. Thank you. All right, so, nice.
You said that in the second term, there is no row of x prime because the interactions are local. So does this mean that I have to somehow, this is strictly speaking a coarse-grained
Yes.
picture? Where, okay.
That's right. No, it gets back to this notion of hydrodynamics, I think of as defined on length scales larger than some kind of fluid cell, where the fluid cell is large enough that it's meaningful to talk about a density of particles within that fluid cell and not worry about fluctuations. I mean, there is an entire field of kind of including fluctuations in hydrodynamics and you can develop a very powerful theory of that in one dimension, as Professor Spona and others have done. But I don't have anything really prepared to say about that.
Again, things have to locally equilibrate within these coarse-grained scales, but can it be that different coarse-grained cells have equilibrated to different ensembles in the course of the approach to the GGE?
Well, it's a local GGE, not a global GGE, in the same way that in hydrodynamics, there's a notion of like local equilibrium that then evolves toward global equilibrium. So if you like, this is saying that my initial condition, for example, here was local GGE. In fact, it was a very simple, local Gibbs, in fact, but Gibbs is one example of a GGE. So it's like locally thermalized to different temperatures through here, if you like. So it wasn't global GGE. And in fact, because there are no collisions, this equation will tend to stream forever. It doesn't actually tend to evolve toward a global GGE. Things just kind of propagate, yeah.
I see, okay, thanks.
Yes. In general, the particles will just propagate okay, so this velocity, if I start at least with a local distribution of particles, the long time fate is going to be that they're flying apart, and eventually it will break down once the density in a fluid cell gets down to like one particle. So for example, you wouldn't be very justified in using this equation if I only had 2 particles in the whole system or something. So there is a long time breakdown when the density gets too low if a finite number of particles are spreading out to the infinite system. But otherwise, I think as long as you remain at high enough density and this local thermalization is justified, I think this is the correct asymptotic long-time behavior. In fact, that's somewhat, I think, rigorously established, or at least, well, rigor is a strong word. It's pretty well analytically established for this 2 reservoir problem. Let's see. I don't think so. I mean, I think basically a way to put it is I don't think it's any worse than the assumption of collisional local equilibrium in a standard fluid. You might have to cook something up on a ring. So we never did one. We never tried to construct an initial condition whose final state would be global GGE. Well, not really. I mean, I guess if you want, I mean, like even if I put it on a ring, if I wasn't careful, I think, okay, I suspect not, because it is still kind of a ballistic system. So it'd be it might superficially look in a density plot like global GGE, but for example, if I thought about a ring, make it a finite geometry to make it well-defined, then a free particle would just keep marching around the ring. Like maybe a way to put it is, I think this is pretty close to free particle hydrodynamics, and free particles I don't think of as, like if I could have a wave of density that kind of keeps going around forever, if you want. Like if I localized all the particles at one velocity or something. Global GGE, okay. Yeah, well, it would be a good experiment. I mean, if there's we did not study that.
Sorry, but what if you start with a somewhat artificial initial state where the Lagrange multipliers corresponding to the most non-local conserved quantities have been assigned large values?
We haven't tried it, but I think, the nice thing about this formalism in a way is like, let me explain how it works in Lieb-Liniger, but effectively, you are treating all the different conservation laws on the same footing rather than just prioritizing the first few. And I think that's why it works well. So I don't think there would be a problem in principle. So what I mean by that is, what I'm going to claim is that, it's okay that I think of this as kinetic theory, and you could call it, Euler equations, because they're closer to each other in these models than they are in a standard fluid by a lot. So what I mean is, I've used that term generalized Gibbs ensemble. That just means like a Gibbs ensemble with an infinite number of conservation laws. If I wanted to write down, what are these local conservation laws, for Lieb-Liniger, it's easy to write them down. They're big complicated for spin. But for Lieb-Liniger, they're things like, particle density, momentum density, and so on. These first three you recognize from a standard fluid. But in Lieb-Liniger, effectively all the moments of the one particle distribution are conserved. Those are the higher conservation laws. And then the way to understand, kinetic theory, normally you work with a finite number of Euler equations that are some kind of reduction or just the first few moments of the distribution, and the other moments you ignore. But now, in these integrable models, really working with the function is basically equivalent to working with all its moments, under the assumption that the function is positive and falls off at infinity. It's pretty well characterized by all its moments. So in that sense, I think the infinite list of Euler equations would be like working with all the moments of rho, and then you might as well just work with rho. There's the same information in both of them. So in other words, that's kind of claiming that GGE is equivalent to rho, rather than containing less information as it would rather than the Gibbs ensemble containing less information like in a normal. And that may be kind of clear for Lieb-Liniger, but I don't think it was something that was very clear for XXZ. And there are these nice papers, the one by Bertini et al. That I cited already kind of shows that, in a sense, even though the charges are very deep and complicated for XXZ, hydrodynamics kind of knows about them. So yeah, this is maybe what I was saying about there's a quench period when I go from some arbitrary initial state to local equilibrium, and then there's the hydrodynamical regime, and then in principle there's some long time dilute breakdown if I'm expanding out to infinity. So now's time to come to maybe, okay, so I think that's where I'm going to stop talking about this sort of Boltzmann-like equation in the easy plane case, because the recent work where we don't have quite the same level of theory is about the Heisenberg point. Heisenberg point, you might think it should be easier because it's higher symmetry, but it turns out that the dynamics at the Heisenberg point are, at least for 2-point correlations, a realization of a famous problem or universality class from soft matter physics. And that came as a fairly big surprise when the group Lubatina, Prozin, and Zadarich published it. We thought it was too good to be true, so we kind of spent a while trying to reproduce their calculation and then to figure out why it worked and everything, but I have been convinced, and the experiment also says the same thing. So I'm going to come to the Heisenberg point, but this works basically for easy plane. Easy axis is diffusive for spin, and the Heisenberg point will turn out to be something quite special. So onward. So that's the paper I mentioned in 2019. This is looking at the thing that would basically be Gaussian if I were to look at ordinary diffusion. So it's Heisenberg chain at infinite temperature, in a sense, random initial condition if you want. And what you get for the 2-point spin correlator collapses well under the Cardar-Parisi-Zhang scaling function. And ignoring the details of that curve, the key relationship, if I convert that, this would be like x to the 3/2 over t. This is dynamical critical exponent z equal to 3/2. So halfway in between z equal to 2 diffusion and z equal to 1 ballistic. And I'd say that we have high confidence in this statement. And even like a calculation, we have moderately high confidence that the 2-point correlators are KPZ. And the question of whether all the behavior is KPZ is what I want to close the discussion with in a couple of slides. So what is this KPZ thing? So Cardar-Parisi-Zhang wrote a very beautiful paper. Actually, my first introduction to this paper was when I was first in India. It was, I was between college and graduate school, and I was a student at TIFR learning from Deepak Dar. And I thought this was a very beautiful paper. I did not accomplish anything particularly in that year. I mean, I learned a bit, and I got to see parts of India and so on. So I had a great time, but I learned a few things, I guess, that came in somewhat handy later. This is diffusion. This is maybe a leading nonlinear correction I can imagine adding to diffusion. And once I add that, then that's enough to change the universality class from z equal to 2 to this KPZ behavior. And it happens all over the place in soft matter physics. It even happens in some other ways in hydrodynamics of various systems, things like asymmetric exclusion process and so on, but it also happens in the spin half. I should have said quantum Heisenberg chain. It doesn't happen in the classical Heisenberg chain because the classical Heisenberg chain is not integrable. So one reason why this is nice is that it gives you a very simple thing to look for in experimental systems, because it's not just a different kind of correction to ballistic behavior, it's actually a different scaling. It says that your excitations should basically move faster than diffusion, the green curve, but slower than ballistic. So, as I said, we spent a while trying to understand what they had observed and figure out when it happened and so on, and this is basically the conclusion of that work. This is with Maxime Dupont, now at Rigetti. If you have easy plane, that is that Lieb-Liniger type case, that's what I mean by, Boltzmann type case, that's what I called a nice physical picture of generalized hydrodynamics. It has a non-zero Drude weight and ballistic behavior. Diffusion is what happens, I mean, actually I would say the diffusion is pretty non-trivial, but it happens once you're over in the Ising regime. And it also happens in a more trivial way if I break the integrability. And this behavior in between, sometimes called superdiffusion, it turns out that it requires integrable models with short-range interactions, I'm assuming that, and a kind of isotropy of the spin. So in other words, something like a non-abelian symmetry like SU2 or higher. So we did a bunch of other models like the integrable spin 1 models that are either SU3 or SU2 level 2, and confirmed that this behavior happens even in more complicated models as long as you have integrability and spin isotropy, but it doesn't happen if I go to inverse square models, for example. So to try to, to give a picture of what KPZ is, this is sticky Tetris. This is what video games were like when I was in high school. So the particles fall down from the top and stick to each other, and it makes an interface. And the interface is clearly moving up linearly in time. But if you were to look at like the width of the interface, sort of if I took one point on the interface and went some distance away and asked how far had I gone vertically, you wouldn't see kind of central limit theorem or Gaussian fluctuations. You would see powers like 1/3 or 2/3 that are characteristic of this KPZ universality class. Now we come to, does this have anything to do with reality? Because the real world is rarely integrable, or maybe never integrable. So can you see some signs of this in the real world? And it turns out, even though all this happened fairly recently, there are 3 different kinds of experiments that all, none of them is perfect. All of them suggest something that is neither ballistic nor diffusive and is most consistent with z equal to 3/2. So the old-fashioned one, the only one of the 3 that I was involved in, was this potassium copper fluoride. And I'll tell you just a sketch. I realize this is the Center for Theoretical Sciences, but I will sketch very briefly what they did. This is a 3-dimensional crystal. It has spin chains in it in the sense that the interactions along a chain are about 20 times larger in magnitude than the interactions perpendicular to the chain. And along a chain, it's well described by the spin half Heisenberg antiferromagnet. So the claim is that something about the dynamics of this should show z equal to 3/2, and that's a bit of a bold claim because this material had been studied for 40 years or so with neutrons, and I'll tell you maybe the highlight of that was some work around 2007 showing the existence of spin-ons. But what we're talking about, this is like real space and time spin correlators. So these are like the derivative of the height field in that noisy Berger's equation. The transform of those is basically what people measure in neutron scattering. So the way it connects to what people had done in the past, the way that people mapped out the border of the spin-on continuum was to go to low temperature and high energy loss of the neutrons, basically high frequency in our spin dynamics. If you want hydrodynamics, that's a long time limit, you should go to low frequency. And you should also do the experiment not at very low temperature. I'll talk about, I think I have one slide on the temperature crossover in a second, but basically, one way that this KPZ regime is unusual is that it's actually the high temperature limit of the spin chain. So we went, usually you wind up begging experimentalists to go to lower temperature, but this was begging them to go to higher temperature, even up to like room temperature, but to look at low frequency. But they were willing to do that. And here's what I meant about a thermal crossover. And this is the spin-spin autocorrelator, like what you measure in an NMR experiment, also shows this kind of behavior. So basically, If I go to high temperature, I see very rapidly an onset of the t to the minus 2/3 behavior that is the hallmark of KPZ, or at least anything was equal to 3/2, I guess. If I go to low temperature, you've probably heard that the low temperature physics of spin chains, of gapless spin chains, is this beautiful Tomonaga-Luttinger liquid theory, but that is a ballistic theory, or a z equal to 1 theory. It's like a free boson CFT. So how do you get z equal to 3/2 universal behavior out of this theory? Well, the answer is the things that are left out in this theory, because they're irrelevant as you go to low temperature, actually matter for the dynamics if you wait long enough. It's an example of dangerous irrelevance, because that free boson theory has no relaxation. You could say its relaxation rate is 0. So even if the perturbations that you ignored because you thought they were irrelevant, if they give you a relaxation rate of some quantity that is non-zero, then you shouldn't ignore them. They will dominate the relaxation rate even though they are irrelevant for the free energy. So the consequence of that, briefly, is that at any non-zero temperature, you just have to wait a time like 1 over temperature for the crossover from z equal to 1 to z equal to 3/2.
So, Joel, quick question here. Is this a general requirement that if you go too low a temperature, some dangerous irrelevant essentially comes in and blocks your any observation of manifestation in any system?
I think it depends on, I think it's most common in 1D, but there are things like it that happen in 2D. So I think it depends on whether the transport coefficients of the theory, including all the relevant pieces, are 0 or are special. So for example, in 2 plus 1D, one thing that like Subir Sachdev has worked a lot on is there you can have a quantum critical theory that has finite transport coefficients, and then this wouldn't happen. But in 1D, most of your critical theories are conformally invariant theories, and those tend to have kind of diverging, the relaxation rates are 0. The theories are kind of ballistic. So in 1D, I think it's generically true that the CFT will effectively be ballistic, but that at non-zero temperature that will get corrected. In 2D, you don't necessarily get ballistic behavior in the same sense, even for a conformally invariant quantum critical point. So 1D is kind of special, but that's a good point. Anyway, so now on to experiment. So this is saying that over some very limited range of about 1 decade, you can get a fit between microscopic simulations of a Heisenberg spin chain and what is measured by the neutrons. If you try to extract power laws, here is the data set from the paper. You get, so I will break a rule. Normally, you should never fit an exponent with less than 2 decades of data. This is 1 decade of data. So if you happen to be an experimental grad student, don't do this. You get 1 decade of data, and therefore you get power laws that do, move around depending on the temperature. But this is, maybe surprising that you can see this quantum dynamics at this large temperature range in a big hunk of material. But the values of scaling that you see are much more consistent with minus 3/2, which is the theoretically predicted value, than they are with either -1 or -2. So I wouldn't call it a proof, but I would say it suggests that something about the dynamics of these Heisenberg spin chains is KPZ-like. And this was done in a big chunk of solid, but very soon afterward, I think less than a year afterward, there was a very different kind of experiment. Yeah.
One question about the experiment. So if the experimental setup is not exactly the integral spin chain, but still you get reasonably good KPZ experiments, could it be that the experimental material has integrity breaking terms but spin preserving terms? Because we know that if you break integrity and preserve spin symmetry, KPZ may still be robust. So why is the experiment so good?
Yeah, I mean, so the experiment is at least good in a sense. I will tell you, I don't know if it's very good for the reason you described. So yeah, I think what Manas is pointing out is the following situation. So if you ask, let's say that I've got the J I wrote down, plus some J prime times some integrability breaking terms, and I ask, how much does J prime matter? Or if you like, one way to phrase that is, at what time scale does J prime begin to mess up the integrability? So because J prime over J here is about 20. So your first guess might be that does that happen at T, let's say that, let's take numbers for this experiment. I could take J over J prime J is 1 over 20. So one possibility is that the time where things break would be like 20. This would be like the worst case allowed by quantum mechanics would be that I get a perturbation that acts at something like 20 times the time corresponding to J, say h bar over J. That would be what I would call bad, and that doesn't seem to happen in experiment. More plausible, and what we think happens for sort of general perturbations that, say, break SU2, is that there's like a Fermi's golden rule picture where the rate of changes induced by this goes like the square, and that would give me something like T, of order 400. But there is a special case, so that's what I mean by good. And what would be very good would be that if the perturbation respected SU2 invariance, then there's a nice argument, not by us, but we did some numerics and we believe it, that instead of going like the square, so I'd call this, Fermi's golden rule, you can get something that goes like, J over J prime to the power 6 if SU2 is preserved. And so then I would get, 20 to the 6, which is a bigger number. So the experiment, I think, is good enough to say that this probably isn't happening, but I think this could be happening because the experiment, neutrons, it's not a very long time experiment. So I don't actually think you could claim that it's this, which I think was your suggestion, but I think it is at least this. Yes, because we have to add terms that make it integrable. So in other words, if I take you have to add things like, let's say, lambda so if this is +1 or -1, so if I didn't have this, it would be gapped and not integrable. If this is plus or minus 1, it turns out that those are both, and this is my memory. If I get a numerical factor wrong, it's possible. But if this is plus or minus 1, that gives you the two integrable gapless spin chains, which are, one of them is SU3 level 1 and one of them is SU2 level 2. Good. So on to the next experiment, which was ultra-cold atoms. And this was quite amazing because you sort of build a system that corresponds to about 50 spins and you watch it go. And even though that's a smaller system, it's very tunable because you make sort of tubes of atoms in an optical lattice, and you can let the tubes talk to each other, so you can study the 1-dimension to 2-dimension crossover, and it's not integrable in 2D. So you find that quite rapidly, once you break integrability, you lose the KPZ physics. So that's sort of a different probe that lets you see, again, z equal to 3/2. So the one that I thought I would mention as sort of exciting potentially for the future, so a special thing about this problem, mostly for quantum condensed matter physics, we don't care about the high temperature dynamics that much. It's not really, most of what we think about. I'll talk about typical quantum matter at the end of this lecture or the beginning of the next one. But quantum computers are not good at cooling down to low temperature quantum matter, but they are good at evolving pure states. The algorithms for that are quite simple, and infinite temperature means starting with a random initial state. So Google Quantum AI, with their machine of 100 or so qubits, and IBM has done a similar thing, we're able to show that something about this problem is KPZ-like, but maybe more interestingly, some higher, it's really starting with the domain wall boundary condition and watching it evolve, but I think the interpretation is that higher point correlators are not in the same behavior as conventional KPZ. So that is a calculation, it was inspired by previous classical work, and I should say that, among the 180 authors on this paper, so that's why I didn't write them all out, but it includes Tomas Prozin and Vedika Khemani, who I think were the sort of condensed matter people who suggested or helped guide them that this would be a problem worth looking at. You can do, if you have other dynamical problems at high temperature, it's a strange era where for a long time as people built these machines, they were quite secretive and they did all their work in-house, but now they're actually looking for suggestions about what to do with the big quantum machines. And this is a problem where, it's a problem that I cared about anyway, and where a calculation done on a quantum computer has somewhat contributed. But again, to be honest, you could say it was really work on this classical Ishimori chain that suggested that this would be an interesting thing to do. So we still get a lot of intuition from classical physics and from our usual analytical methods, but at least we might be in the age when quantum computers actually contribute to some science. And again, just to kind of my last computer sciencey slide, one reason why they care, I said, was you could make something, if you're allowed to change the couplings, you could make something that would be more powerful. You actually get even more powerful. These are complexity classes that we think are much more powerful than even the best quantum computer. So we think it's going to be impossible to find the general ground state of something like a Heisenberg model, but impossible to a higher degree than finding the ground state of the random Ising or classical model. So somehow, these are sort of statements for complexity theory, but one reason for building the machine is that you can play around with it and try to understand when does the hardness onset as you go from like uniform systems to random systems. All right, so I was going to, and sort of the public lecture spirit, but I think I'll skip it, talk about not so much the algorithm, but the magic that makes this possible is to me one of the most amazing things about quantum condensed matter, which is that basically a big superconductor behaves like a single quantum degree of freedom. And that's already been sort of useful. Quantum devices have been around since the 60s. This is a very small quantum computer from my home institution. But the reason why it works is that, and this is where, if there was going to be a physical breakdown of quantum computing, I suspect this is where it would have happened. So the encouraging thing is that it hasn't really broken down yet. You can describe, a superconducting loop with some breaks in it extremely well with a single quantum phase variable, and describing billions of electrons and so on, and making superpositions and sort of re-quantizing, treating that phase variable like another quantum variable seems to work. So that's heartening, even if so far, 99% of problems we can't really do. So that is where I wanted to stop talking about quantum computing and talk about a problem that's more on the standard frontier of quantum matter. And I don't think I'll get through it today, but I can at least get started. And fortunately, I have one more lecture, so I'll get to cover it more. But just to kind of explain how the three lectures fit together, in a way, I talked about emergent gauge fields, Berry-type gauge fields in the Brillouin zone, and about light and electromagnetism a lot in lecture 1. Lecture 3 will be about quantum information as a tool for condensed matter. What I want to talk about in closing is when you go to higher dimensions, even that same Heisenberg spin Hamiltonian gives you very complicated behavior. And trying to find a particular kind of spin liquid with an emergent gauge field that is actually dynamical and has things like monopoles and so on, that would be sort of a holy grail that we're still pretty far from, but I can talk about steps on the way. We're at least closer than we were a couple of years ago. So I think I'll wind up a few minutes before the allotted time so that we have a little bit of time for discussion, and then pick up a little bit next time. But just to explain, things aren't actually much more complicated than what we talked about before. This is the same Heisenberg Hamiltonian, but if I put it on a different lattice, like this Kagame lattice that applies in this material, then it's suddenly very hard to find the ground state. So for example, people don't really agree on the ground state of the Heisenberg spin half antiferromagnet on the Kagame lattice. If it's a spin liquid, if it has a gap, whatever. Just to remind you where this comes from, this interaction is the leading term in perturbation theory for a Mott insulator, which is a state where I started with, say, a metal, non-interacting electrons at half filling on a lattice model. I turned up some local repulsion between the electrons. That becomes an insulator. And this is a spin interaction, not the only one, but the leading one, deep in the Mott insulator. Our idea for how to sort of rehabilitate Phil Anderson's original proposal is to think on an even simpler lattice, the triangular lattice, as we go near the Mott transition, so still insulating, which means still a spin Hamiltonian is valid, but with additional interactions, do you get anything more complicated? And the various things we'd like to create are new kinds of quantum matter. I mean, some kinds of spin liquids, including the one that is going to come out in that Hubbard model, are very closely related to fractional quantum Hall states and topological order with anyons, which you've heard a little about earlier in this meeting. So sometimes people use fractional states to try to build quantum computers. That's been a big project at Microsoft for 15 years. But I want to talk about topological states sort of for their own sake. So what I want to claim, and I'm only going to do the first part in these lectures, is that the Hubbard model, simplest model you could write down for correlated electrons in the triangular lattice, has a kind of spin liquid that is not the one we expected, and it's also not where Anderson told us to look. And that's originally from numerics, but we have an analytic picture now for what's going on that I want to tell you because I'm kind of excited about that. And then probably next time, there is a bit of a materials breakthrough. There are new families of ytterbium-based triangular lattice compounds that are right now the best active candidates for spin liquids. And in particular, maybe this long-sought Dirac quantum spin liquid that I'll talk about next time, but maybe not. And that is sort of the frontier of the field, so that'll be a good place to stop. So let me tell you what Anderson's original idea was, and then why it failed, and where you could look differently. So this is the Hubbard model. Put this on the triangular lattice, and what we now believe, I think what everyone believes, is that if I go deep into the Mott insulator, which means large U over T, then I get conventional long-ranged order of 3 sublattices. U over T, basically the system goes Mott insulating at about U over T equal to 8. If U over T is between 8 and 10 or so, then you get a gapped phase. So it's gapped for charge because it's a Mott insulator, it's gapped for spin as well. And first, this is the numerical paper that got us interested in trying to understand why. And other people have since, for the most part, seen what we saw. There is an interesting state in this model that breaks time reversal symmetry, has edge states, and is very much like a spin version of the fractional quantum Hall effect. If you like, it's the Kallmeier-Laughlin chiral spin liquid. And why we know that, or why we believe that, is some deep numerical analysis, or why we believed it then. But let me give you instead a sort of physical argument for why that is a reasonable thing, and then how we can check that argument, again, with a little bit of numerics. But just to kind of a little bit of pedagogy or overview of what's going on, there are many different kinds of spin liquids, and there are at least 3 that are going to appear when I talk about them. And again, this is a problem like the hydrodynamics one, where some people here are experts and some people won't have seen it very much. So let me give a quick slide and then tell you, my friend Roderick Müssner wrote a nice field guide to spin liquids, and it's in here somewhere, chapter 5, so if you want, you can read more. But here's the intro. The kind of spin liquid that Anderson originally proposed, we would now call a Z2 spin liquid. This is the one that's like floating dimers or resonating valence bonds. It has time reversal symmetry, it doesn't have an edge state, and you can make a sort of artificial Hamiltonian on the triangular lattice that will have it. Chiral spin liquid is like the fractional quantum Hall effect. It breaks time reversal symmetry, it has an edge state, and Kallmeier and Laughlin proposed it for the fractional quantum Hall effect, but not with a very physical Hamiltonian. Then the ones that are more mysterious and kind of hard to categorize are spin liquids with no energy gap for the spin. And that's where maybe the frontier or the mystery is that I'll lead off with next time. But when we started the triangular lattice, we thought, based on sort of early generation numerics by other people, that we would see lots of low energy spin-ons, spin-on Fermi surface, but that isn't what we found. And let me try to give you our understanding of why, what is important for the physics near the Mott transition and what it gives you, and I think that will be good for today. So the first message is that the Hubbard model is probably not an exact description of any material unless you use ultra-cold atoms to build it. And frustrated magnetism means in general that things are happening at small energy scales compared to J, and small perturbations rapidly change the energy scale. Rapidly change the state, because you have a lot of competing states. So what are the perturbations beyond that nearest neighbor Heisenberg coupling that's always the largest? So this coupling dominates because it's order t squared over u. I mean, that's the one part. Then here, I've got J2, J3, J4. This is second neighbor, this is third neighbor. You can see their coefficient is 4 t to the fourth over u cubed. But it was known for some time for series expansions that the most important coupling is the one that's kind of painful to deal with. The most important coupling after the nearest neighbor is J4. So if you want to describe the Hubbard model, you shouldn't really do a J1, J2 approximation. You should do a J1, J4 approximation with this 4-spin term, but that's rarely done because the 4-spin term is kind of messy. But I will tell you a way to rewrite the 4-spin term to make clear what it does and why it might like the chiral spin liquid. And then I'll talk about materials next time. So the basic idea, and this was with my student Tessa Cook-Meyer, is that there is, even though if you stare at this, it's not immediately obvious, for spin half on the triangular lattice, there is a unique way to rewrite this as an expansion in the scalar chirality, which is this product of spins around a triangle S1 dot S2 cross S3. So in other words, there's no freedom in this polynomial of the J4 term and the chirality. And then if you look at this polynomial, these coefficients, you can imagine that we checked this calculation in Mathematica and so on. These coefficients are not particularly intuitive, but at least the sign, you might think that there's some physics in that, because note that the quadratic term and the quartic term are negative, and then the sixth order term is positive. That means that you lower the energy by having some chirality. So that means that even though it's not obvious to look at it, the effect of the 4-spin term is to favor chirality. And I mentioned before that the Kallmeier-Laughlin state was known to be the ground state of a not very physical Hamiltonian. It's a Hamiltonian where you've imposed a chirality to break symmetries. So effectively, there's a 2-step process going on where 4-spin terms lead to spontaneous breaking of symmetry. They give you a chirality. Chirality gives you the Kallmeier-Laughlin state. So in other words, a 2-dimensional system of this type with a scalar chirality and quantum spins tends to go into a topological state with anyons. So that, I have more to say about what happens in experimental reality, and just so I don't want you to come tomorrow on false pretenses. The experimental reality does not, so far, detect a chiral quantum spin liquid. It detects something that is maybe more interesting but more nebulous. So I'll talk about experimental reality for tomorrow, but I think I'll stop there just so that we have time for a few more questions, either about the first part or the second part. So I think that's enough for me today. Thank you.
Do we have questions?
Regarding this last part of having finite chirality, so is there a construction where I can understand this chiral spin liquid as really the bosonic integer quantum Hall effect of these bosonic partons like Schwinger boson construction, where the chirality produces the magnetic flux?
That would be interesting. I haven't actually seen a calculation trying to do that. Maybe, I mean, did like Schrieffer, was there, in the early days of the chiral spin liquid, was there something like that?
No, there's a calculation on the easy axis Kagome lattice like that, where because of the easy axis, you again have these chirality terms, and you can think about this as a gauged bosonic integer quantum Hall effect for the Schwinger bosons.
No, interesting. That I haven't tried. I mean, I can tell you what we did to try to confirm this scenario. Is that you can ask, okay, so suppose you're doing mean field theory of something simple like the classical Ising model. How do you know, not exactly that it works, but how do you know that it's at least self-consistent? The idea is, the self-consistency step is, you put on some field from the neighbors, you figure out the moment on your site, and then you ask, you've reached self-consistency when the moment that you get on your site is consistent with the moment you assumed on the neighbors to generate the site. Mm-hmm. So you can do a kind of DMRG powered mean field, which is actually, I think, a coming computational technique that we also do for things like superconductivity, where you take this exact decomposition of the Hamiltonian and then you approximate it by saying, let me take some value of the chirality, calculate the Hamiltonian in that chirality using DMRG, and then pull out the chirality from that calculation and iterate and see, is there a self-consistent solution? And it turns out that there is a self-consistent solution basically exactly for the range that the chiral spin liquid seems to be stable in the unbiased calculation. So we can do a kind of check that at least the mean field picture of ordering in the chirality is self-consistent. But that doesn't, of course, that doesn't rule out some other ground state.
Okay. Yeah, thanks.
J4 term, what are the spins that you were coupling in the lattice like that?
Yeah, it's around a parallelogram of two triangles.
I see. Okay.
Yeah, that's right. So yeah, I should have drawn that. I mean, it comes up a little bit, yeah, when I write, so for example, the chirality, the way it's related to the chirality, again, it's a little bit of algebra. This O operator, that's directly the chirality. So chi squared is product of, one upward facing triangle and one downward facing triangle. So there's a lot of geometry and spin operator algebra that, as far as, unfortunately, we were excited when we did this that there would be other applications, but it only seems to work out so nicely for like the triangular lattice, basically. Doesn't work as well for the Kagame. Anyway, but yeah, so the two triangles making up of one parallelogram is kind of the key object for this.
Thank you.
You say a little bit more about the precise definition of the complexity classes for quantum algorithms?
Ooh.
You had this stochastic Q. Yeah, that one. This one. The lower.
So I guess, the stochastic MA, this is related, if you like, to, okay, I can give you a very heuristic answer, and I think for the truth, you'll have to consult a real source. But I mean, this class of problems, stochastic is related to, effectively, you could think of it as problems where there's no sign problem in quantum Monte Carlo. It's probably a way to state it. So they're still kind of quantum mechanical, like I would say. This is classical. This is, if you like, classical in a higher dimension, or it has a representation that gets rid of minus signs. And this is truly quantum. It's maybe the way to think about how the three are different. And this stands for quantum Merlin-Arthur, and is sort of defined in terms of resource to an oracle who will do things, some things for you and not others. But I'm worried that if I tried to explain it, I would not get it correct. So.
I have a very naive question. So this complexity, as you said, this computer science community, they believe that P will not be NP. There is a no-go that P cannot be probably, most of the belief is P is not NP. So this is a no-go theorem, no-go statement. On the other hand, physics also we start with some no-go theorem like second law of thermodynamics. It's a no-go result. On the other hand, relativistic causality, no instantaneous signal is possible. Do you have do you think there could be some physical justification to believe that P is not equal to NP?
Well, let's see. I don't know about that, but I do know that there's a sense that some complexity classes, like, okay, well, the one kind of foundational or philosophical question like that I know people have thought about a lot is, what is the hardest problem that nature can solve? From a computational point of view. And that would be like a physical limit on some computational classes. Some computers are more powerful than anything we could build that is local in our universe. And I think that gets into actually some of these discussions, like, there may be a sense that I've at least heard arguments that no local quantum Hamiltonian is going to, like finding the ground state of this in a short period of time or something for arbitrary interactions is not only not going to be possible for us, but it's not going to be possible for Hamiltonian evolution. So the normal Hamiltonian evolution would be obviously constant energy, but you can imagine that you're coupling the system to a bath and our usual approaches to cooling. I guess there is a belief that some computational classes are actually unphysically powerful. P and NP, I don't think there's that belief about NP, and clearly P is, humanly powerful, or not that hard. But so I don't know. I don't think there's any physical reason to believe that NP is not equal to P. It just seems to be an enormous amount of experience. But I suspect that if you like some of the harder classes, people, I guess, who think about these things find it very hard to think of a local quantum process that would accomplish this for you. So in that sense, they seem more powerful than any quantum computer or any physical computer.
Thank you.
But yeah, I will say, just mentioning this age of quantum information theme of the conference, an example of how there is some interesting synergy. Like I go to these meetings and there are more things that sound neat to work on than any one person has time. Cooling is hard for us in condensed matter. If you go to Arendam's laboratory and they try to get something down to very low temperature, it takes time because the thermal conductivity always goes to 0 at low temperature. So it takes more and more time to get the energy out. So people doing quantum computing are now thinking a lot about, if you have a quantum computer, what's the fastest you can get matter cold? Because they would like to study ground states and do quantum chemistry and quantum matter problems and so on. So it seems like fundamental limits on cooling and trying to do sort of quantum dynamical Glauber dynamics and things like that, and versions of sort of quantum processes intended to cool rapidly, and whether is the way that we cool, which is like putting a system in thermal contact with a cold reservoir, is there something that's kind of optimal about that, or is that very far from optimal? That is the sort of problem that I see discussed at conferences now.
So this is about the Google's calculation measurements. So they had found that the higher cumulants of the KPZ problem or the Heisenberg problem do not agree with the KPZ scaling. Do you know if that is due to the noise in the measurement, or is it something that?
I don't think so, because I think it also happens for there's this Ishimori chain, which is like classical unit. So I mentioned that the Heisenberg, classical unit vector chain is not integrable. But if I took a chain that was like, so now these S's are just unit vectors. That is the classical model that has a lot in common with this quantum Heisenberg model. And I believe that the quantum Heisenberg model domain wall dynamics that have puzzling higher moments, I know that they were at least inspired to do that by work of people like Prozin on this kind of model. But I don't know that they're exactly the same, but I think that same problem arises here. So in other words, I don't think it's a mistake because of the noise in the computer. It's a bit, it may be a better, what is a universal, what behavior is incorporated in universal class, in universality class? I mean, I don't know whether you should take it as meaning that the whole thing is just in a different problem than KPC, but the two-point function happens to agree. That seems a little bit much. Or it's more that you can, push the system hard enough to see some behavior that is different from what we think of as standard KPZ behavior, but the most important quantity, like the linear response quantity, is still KPZ. I think there's some interpretation there, and I don't know which side I'm on. But at least I suspect that it is a correct result. I mean, there is certainly noise in the machine, and a lot of the hard work, I mean, the reason why there are 180 authors doing a lot of work, aside from all the hardware engineering, there's a lot of coding that is like coding a computer, a normal computer in like 1948 or something. There's all this little tweaks to get rid of errors locally and so on. It's a lot of work to program a current quantum computer to do anything interesting. They're working on compilers and stuff like that, but if you want to push the envelope, but anyway, I think they've done a reasonable job of getting rid of noise, and I suspect the result is correct.
So maybe I had two questions. So one was like, so I guess this KPZ is not completely understood, right? Why you get KPZ? But there's been a number of proposals, like including this kinetic theory of these sort of solitons, which are these bound states having lifetimes, and then there's this fluctuating hydrodynamics and so on. I mean, like, do you have any comments on like what you think?
Yeah, I can tell you some things that work. And some things that don't. I mean, the main effort I know, there's a long paper by Sarang Gopalakrishnan and Raman Vasur, which is trying to understand the differences and make a model for the higher point behavior and so on. But and I think they accept that it's sort of close but no cigar. It's a useful model, but it doesn't seem to be exactly what's going on. So I don't know a model that gives the 4-point, but maybe there is one. But if it happened, it was just in the last few months or something.
See KPZ, I mean, even that.
Yeah, so the only thing that I trust is there is a calculation of z equal to 3/2 that is almost like asymptotic analysis of the beta-ansatz solution, but that doesn't give you a KPZ scaling function or anything. So in other words, I think it's easier right now to compute z than it is to get the full scaling function, and that makes me think that maybe there's some problem in the full scaling function calculation that we don't know how to do analytically. Anyway, I think that's where we are. I mean, the paper, there are 6 authors, and the first one is Inez Ilievsky, is the one that sort of makes a pretty serious effort to use beta-ansatz asymptotics to calculate z. And in fact, it claims that they've done it not just for Heisenberg, but for anything with our kind of conjecture conditions, which is, short range, a non-abelian symmetry, and integrable. No, it's called, I think the title is something like Super Universality of Superdiffusion. But yeah, it doesn't exactly, I don't think it, as I recall, it doesn't claim to derive KPZ per se. It might say a little bit about that, but mostly, I mean, the part that's a real calculation is about z.
The other question was in the Google experiment somehow, I mean, did they actually also verify the KPZ scaling function?
I don't think they saw anything that was inconsistent with 2-point. I mean, the way I think they did this domain wall initial condition, so I'm not sure. I don't recall a figure of the 2-point in their paper, at least. But I mean, the 2-point, it's kind of interesting. It gets, because there's so few qubits, like maybe a way to put it is, for many of these calculations, there are many things that should be the same theoretically, but one of them is easier with current hardware, with current system sizes and things like that computed. So for example, the domain wall, we started using the domain wall for some things because it approaches its asymptotic limit more rapidly than the standard calculation of the 2-point or something like that. But I mean, all I can say is, at least at the level of DMRG, I haven't seen any calculation that suggests that this agreement is accidental. I mean, I think, I think most of the calculations, even up to now, are kind of like I doubt that the quantum computer could do this any better than the classical computer. And the situation is going to be that, the central peak is pretty similar, but when you're out in the tails, things are kind of noisy. I don't think there's a huge improvement on that.
Okay. One question from Marcel.
So I have a question which is based on, trying to understand the origin of this KPZ. Is this related in some form to some moments which is also related to entanglement? So if I look at the mutual information after a quench with this initial condition, can I see these dynamical critical exponents which are different from ballistic and diffusive also in entanglement related quantities or not?
I don't think so. Basically, there are a lot of situations where ordinary correlation functions can be diffusive, but entanglement can be, ballistic. And I would suspect that these are going to be in that class. So for example, energy transport is ballistic, and that makes me think that there's something that is ballistic in the system, and that will make the entanglement be ballistic. So I'm not, my guess would be, you would have to define some very carefully chosen entanglement quantity to get something like the 3/2 superdiffusion. I think most natural quantities will give you ballistic.
But it can exist.
Yeah, I don't know any way to, I don't know any to rule it out. Yeah, but if you want I think we don't have a very good picture for. I guess I'm aware of efforts, but just a picture that would give like a satisfactory. I mentioned the work by Gopal Krishna and Vassur. That's an effort to understand why might it be that 2-point is KPZ and higher point is not, but it gives a picture of the higher point that doesn't seem quite right. So I don't think we have a great derivation of KPZ. As I mentioned, the thing I think that is most reliably derived is equal to 3/2. I would say we mostly have numerics for 2 and 4 point functions. And yeah, I don't think I have anything to add to what I said. But yeah, I mean, it's very, it's impressive that this 80-year-old problem turns out to be so subtle. And even the easy plane case, once you get away from expectation values and look at fluctuations and other things, even the easy plane case has a lot of very rich behavior. It's much deeper than that little Boltzmann model I put, if you ask the right questions. So it's kind of a renaissance of spin chains, I guess.
One last question.
Joel, the Heisenberg model has this non-abelian symmetry. So in case of, let's say, things like MBL or, where it didn't exist, there was some picture about how the fact that you had this non-abelian symmetry gradually led you not to have a, let's say, MBL exactly at the Heisenberg point, some picture, not just... Is there a picture like that you have, how the non-abelian symmetry is important?
I have a picture for how the non-abelian symmetry is important, but I'm even on the right side here, but I don't know that this is I don't know it's a right picture because it doesn't lead you to anything you can test. But the idea would be, suppose I had, okay, if I have a model that is close to order, these models are kind of power law ordered, then I would be inclined to think of it as some kind of sigma model description where like the order might be on a circle for U1 or on a sphere for Heisenberg. And if I think about a circle or even a product of circles, and I think about the sigma model that I write down, the sigma model into the circle doesn't have, you'd get grad theta and grad theta squared, and theta would be periodic, but there's no interaction in it. But if I take the sphere, the fact that the sphere is curved, has Gaussian curvature, gives me an interaction. And I suspect, if I had to make, the only simple picture I can think of for why the sphere gives you KPZ and you don't get that kind of interaction is just, there's a nonlinearity here, and there's a nonlinearity on the sigma model in the non-abelian case. But whether those are the same nonlinearity is just speculation.
We can take the next questions probably over to the coffee break. So with that, let's thank Joel again.